Hello everyone and welcome to another video. Today I'd like to talk about one of the most popular and powerful control design techniques around, the linear quadratic regulator or LQR controller. We're going to see that an LQR controller is effectively a full state feedback controller where the gain matrix K is computed in a very particular fashion. I'm going to assume that you're a little bit familiar with full state feedback control, but if you'd like a quick refresher, please check out this previous video where we introduced full state feedback controllers. We're also going to see today that LQR controllers address some of the practical implementation issues we encountered when designing full state feedback controllers. So to get the most out of the discussion today, I recommend that you also check out this other previous video where we discuss some of these implementation problems. Links to both of those videos are in the description below. So if all of this sounds like more fun than a clown on fire, let's jump over to the whiteboard and get started. All right, so let's talk a little bit about the linear quadratic regulator, or LQR controller, right? So, like we said earlier, the deal with an LQR controller is that let's assume that we've got a plant here. It's a linear plant of our standard form here, but the output, like we said earlier, is the entire state of the system. So if you have this scenario, we said last time that pretty much the most powerful controller you can use here is a full state feedback controller like this, right? So here's your full state feedback controller, right? And the whole game plan at this point was just to choose K. So last time I think we showed here that you can basically try to tailor how the full state feedback controller behaves by choosing desired closed loop poles of that entire system, right? I think last time we said that, you know, if you had some plant here with certain open loop poles here, right, represented by these blue X's here, right? So these blue ones are open loop poles. In other words, it was basically eigenvalues of just the A matrix, right? And what we said later was that, okay, I can just go over to Matlab and I can say place A, B, and some P desired, right? And this would give me a matrix K, or it would give me the controller that would move the open loop eigenvalues, in other words, these blue X's, to wherever I desire it to go here, right? Whereas this P desired. So we saw that by choosing locations of, say I want to move them, you know, something like this here, right? Where these green ones are now my desired poles. These are my P desired. We saw that by changing these locations, moving them further or closer or moving only certain poles, right? We could somehow mess with what value K was. But this was a little bit unsatisfying in the sense that there wasn't a real knob or way to twist and physically understand how the changes of these green X's affect the controller or affect the behavior of this overall system here, right? So that was the problem with full state feedback controller. It was a little bit difficult to understand the relationship between P desired and the resulting K. Well, this is exactly the problem that LQR is going to allow us to address here. What we're going to do here is try to pose this entire problem here in an optimization framework. So optimization is one of the most powerful branches of mathematics. In fact, I've heard a couple people say that, you know, it's probably the most important engineering topic here, that almost any problem in engineering can be posed as an optimization problem if you think about it long enough here. So what we should maybe do here is let's take a brief sidestep and talk a little bit about what is optimization and how can we maybe apply it to this scenario.
So to set the stage for the concept of optimization, let's talk about my daily commute. For those who don't know me, I live in the Pacific Northwest. Specifically, I live on Bainbridge Island, which is about 10 miles west of Seattle, Washington. And I work at the University of Washington, which is actually on the other side of this large body of water called Puget Sound. So the problem I'd like to consider now is, how can I commute from my house to my work every single day? Why don't we brainstorm some possible solutions to this problem? Now, luckily for me, the state of Washington operates the largest ferry system in the United States, so one option is I can just drive from my house down to the ferry terminal, put my car on a ferry boat, go across the Sound, and when I get to Seattle, just drive the rest of the way up to the University of Washington. So let's call this solution maybe Z1, where I drive from my house to the ferry, catch the ferry, and then drive to campus. What else could we do? Well, if I don't want to drive, maybe I'll catch a bus from my house to the ferry terminal, walk onto the ferry boat, and then when I get to Seattle, just find some bus that happens to be going to the UW. So here, that's Z2 here, bus, ferry, bus. What about a third solution? Well, if I want to get some exercise, why don't I ride my bicycle to the ferry terminal, and I can actually put my bike on the boat, take it across the water, and then when I get to Seattle, ride the rest of the way up to the University of Washington. Great. So Z3, bike, ferry, bike. Why don't we think outside the box a little bit? I could maybe now run from my house to the nearest shoreline of Bainbridge Island, hop in the water and swim 5 miles across the sound here, and then Forrest Gump it to campus and arrive more tired than that creepy dwarf in Snow White. But you know what? Z4, where I run, swim, run, is actually a feasible solution. Alright, let's just skip all of this hoo-ha, and I'm just going to charter a helicopter to take me directly from my house and drop me off at my desk at the University of Washington every day. So, Z5 is just charter a helicopter. You know what? This sounds good, so why don't we stop here? Let's call this entire set of all possible solutions the feasible set. The feasible set is basically every solution you would like to consider when solving an optimization problem.
Okay, so we saw that we had all of these potential solutions, and we said we're going to call a collection or a set of all of these, maybe big Z, and we'll just put all of these solutions in here. And this is what's referred to as the feasible set. So now that we have the feasible set put together, the next thing we need some way to measure the goodness of each one of these items in the feasible set. This is what's known as the concept of a cost function. So the idea with a cost function is that it is literally a function where you pass it in an element of the feasible set, so it's one of these z's here, and all this thing's job is, it's got one job, right, is it needs to evaluate how much does that item cost here. Okay, so what will come out of this is, let's call this cost j of z here, right? So again, this is typically, we're going to use a notation j here. So j of z is going to be the cost function that measures how much solution z costs, right? So this could be in terms of dollars or any other abstract metric, as long as it's a scalar value here, right? Where you pass it in an action, and an action, you know, it could be something complicated like all of these, or it could be a vector, it could be some item, right? It's some solution. This thing gives you the number of dollars here, right? It gives you a single value which measures that, right? So what we're going to see here is that the optimization problem involves finding a feasible solution here that will minimize the cost of a given problem here, right? So tell you what, let's consider a bunch of different cases here. So let me erase some of this so we can get a little bit of space. So I'd like to consider a few different scenarios here. So let's look at maybe case or scenario 1 here, where I want to minimize time. Okay, so in this case, what I'd like to do is I'm going to develop a cost function. Let's call it j1 of z here, right? Where what this cost function does is it just measures the time required for action z, right? So in this context, the problem here, or the optimization problem, let's write it here as maybe P1 here, right? Is I want to minimize j1 subject to the constraint here that I'm not going to consider all possible solutions. I only want to consider solutions here that are in my feasible set here, right? Only these 5 that we laid out here, right? So if you look at this, what the optimization problem says is I need to find the element in the feasible set which basically will yield the minimum time for my commute here, right? So if you look at this here, right, we can iteratively by brute force just go through every single one of these and evaluate how long they each take. And the winner is going to be Z5 here, right? You can pretty much see that out right off the bat that this is going to get me from my house to campus in the minimal amount of time here. So in this scenario here, right, the thing that is optimal here is Z5 is optimal, right? Okay, well, how about let's consider another case. How about case 2? Maybe let's underline these so we can keep them apart. Case 2 here. How how about let's minimize money, right? So instead of time being important, let's say I'm super cheap and frugal and I care about money. So I need to develop a second cost function, J2 of Z. This cost function's only job in life here is to measure literally the cost of action Z. Right? So how many dollars does each one of these things cost? So I can form an entirely new optimization problem. Let's call it P2, right? Where I now, same thing, I want to minimize this other cost function, J2 here. Again, I'm only going to look at solutions in my feasible set here, right? So I go through each one of these and I ask, how much does this cost here? Well, it costs me some gas, and then to catch the ferry, I actually have to pay to take my car across. Then it costs me some gas again. Oh, here, Z2. This is actually a little cheaper here because I don't have to pay to take my car across the ferry. I can just walk on, which is actually much cheaper. Ooh, this is also kind of cheap here, but oh, hey, check this out. Z4, this doesn't cost me a dime here, right? I can run for free to the shoreline. It doesn't cost me anything to swim across. Well, it doesn't cost me any money. Maybe let's put it that way. It might cost me other things, but it doesn't cost me any money to get across Puget Sound, and I can run. And ooh, crud, the helicopter is definitely going to cost me a boatload of cash here. So you know what? In this scenario here with this cost function, the optimal thing to do is actually Z4, right? So this is really interesting here in the sense that this same optimization problem, we can change the solution by picking the cost function appropriately. So I'll tell you what, let's go ahead and let's make another variation on this. How about case 3 here? Let's try to look at minimizing a time and money trade-off. Okay, so in this case, why don't I make a cost function, let's call it J3, which is actually a combination of these two here. So let's have J1 here. Remember, J1 returned the time required, and I'm going to add that to J2, which measured the cost here. And what I could do here is I could put some scalar weights in front of these here, which would allow me to sort of trade off between how much do I value time versus how much do I value money here, right? So in this case, Q and R are scalar, let's call them weights, right? That we can use to tune the optimization problem here, right? So for, if you look at this, you can basically see here that depending on Q or R, you can say, do I care more about time or do I care more about money? So just to kind of write this down, right, if you look at this here, well, again, maybe we should write down the problem here, right? So the problem is the same thing. So P3 is now, I just want to minimize this new cost function J3 of Z such that subject to Z is in our feasible set big Z, okay? So depending on what values of Q and R we choose, you probably get different values here, right? So in general, right, you can see here that a large Q relative to R, right, what is that going to do here, right? That's basically saying that you're reverting to a minimum time problem, right? Because if Q is big, then if the time is big, the whole entire cost function becomes big here. So you really want to choose solutions that minimize time here. So if you do this here, this is basically saying you, whoops, I should make relative to R, right? You're super rich and your time is more important than your money here, right? So if you do this, you say what we're basically doing here is this kind of reverts to a min time problem, right? Basically reverts to this case here, right? So we see that, all right, in this case, you end up again back with our Z5 solution of just getting the helicopter, right? Alternatively, if you have a small Q relative to R, right? This is now saying that, no, actually, you're super frugal, right? You don't have any money, so any expenditure of cash is very, very bad here, right? So that means that R is, sorry, where was I? Yeah, R is larger than Q here, right? So what this does is what? This reverts to a minimum money problem here, right? So here, this solution comes back to being Z4 here, right? Which makes sense. Now, where it gets really interesting here is what if you have a trade-off between Q and R, right? in this case, this is a new scenario, right? Where now it depends. It depends how much do you value time versus how much do you value money. So in this case, we have potential solutions. I don't know which one is going to be optimal. Again, it depends on what values of R. But now you've got a Z1, Z2, or maybe Z3 as being reasonable solutions here. All right? Let's explore this a little bit further here. Let's think of maybe a case 4. So let's do this right here. Unfortunately, I didn't manage the board space extremely well here, but let's look at case 4. Case 4 is basically, I'd like to look at case 3 again, right? This interesting situation where we're trading off time and money, but I'd like to add what are called constraints. Okay? So what constraints allow us to do here is further tailor the solution to this problem here by eliminating values in the feasible set. So what this does here is, again, let's restate our problem here. So I'm gonna call this P4 now here, but again, it's the same cost function as case 3, right? So I want to minimize J3, right? This was our trade-off cost function here, subject to elements in the feasible set here. And I'm going to tack on some additional constraints here as something like, what if I say I want to make some kind of requirement here that I need to get 30 minutes of exercise during my commute or more here. So what I'm going to do is I'm going to make up a function, let's call it F1 here, right? Where F1's job here is that you put in an element out of your feasible set here, and what this measures here is it measures the exercise time associated with action Z, right? So the optimization problem becomes what we saw earlier, but as well, I'm going to specify a constraint, like I need F1 of Z to be greater than or equal to 30 minutes here. So this is basically saying that on my commute, I also want to make sure that I get 30 minutes of exercise. What this does by specifying this additional constraint here is we see that it starts making some of these elements in this original feasible set infeasible. So for example, if we look at all of these here, let's just walk down these one at a time, right? How much exercise am I going to get out of each one of these? So Z1 here, right? Z1, if I pass this through my F function, it's going to look and say, hey, you spent 0 minutes exercising because you're just walking in the or driving in the car, then you sit on your bum on the ferry doing nothing, and then you drive some more. So this actually does like nothing. So this is now not going to be allowed any longer here. So Z1 is no longer a feasible solution. Same thing with Z2. You're just sitting on the bus and sitting on the ferry. So F1, this function here, or this constraint that we cooked up, is going to say, no, that's not allowed any longer. Okay, Z3, this is, actually, this is still allowed because you're going to get a lot of exercise biking here on either end. So this is allowed. Oh, man, Z4 is definitely allowed, right? You're probably going to get more exercise than you want here. And then the helicopter becomes infeasible because you don't get any exercise on this helicopter here, right? So suddenly, this problem here now gets a little bit simpler because the feasible set shrunk. So there's only 2 solutions here. You can either bike or run and swim here, right? And usually for most values of R and Q and R, right, you're going to see that Z4 solution, that's going to take hours and hours and hours and hours. So usually this term here, the cost function that's measuring time, is going to make that Z4 solution really unattractive. So in this case here, what's probably going to happen here is we're going to end up with Z3 is optimal, right? So this is really fascinating in the sense that depending on how you tailor your optimization problem, right, the solutions change here. What is considered optimal changes here, right? So this is actually really interesting. And now the question would be, how can we apply this optimization framework to designing a control system for a linear dynamic system? So let me erase the board and we'll jump into that next. Okay, now that we've got that basic understanding of general optimization, let's think about how we can set up the optimization problem for designing a linear quadratic regulator here. So let's talk real quick about setting up the optimization problem. So I always think it's easiest to think about a concrete scenario. So, you know, what if we had something like a satellite here? So I'm going to try to draw a satellite here. I'm obviously not a very good artist. I think those of you who have seen some of my other videos understand that. But I'll just make some little cartoon here for a satellite here. And what we'd like to think about here is this satellite might have multiple states here, right? So the state vector for this satellite might be something like the orientation, right? There might be states for the Euler angles. There might be states for like the position, all these other things, right? We will just stack all these up in the state vector. And at the same time, this satellite might have multiple different controls, right? It might have like a primary thruster here. It might have smaller positioning thrusters or momentum wheels or things like that here. So we might want to also say that this thing has multiple controls here, right? So this would be like the main thruster, you know, electric thrusters, momentum wheels, etc., 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 right? All we're getting at is that this here is a dynamic system which has multiple states and multiple controls. Simultaneously, let's go ahead and assume that this is a linear system governed by dynamics of x dot is equal to ax plus bu, right? Our normal state space representation of my dynamic system, basically saying that the state and the control, they're not free to be anything they want, right? There's a relationship between how the states and the controls interact, and they interact through this dynamic equation here, right? So within this context here, what we want to do here is let's set up an optimization problem here. So the optimization problem here is, let's go ahead and consider a cost function. Let's just call this thing j like we did earlier here, and we're going to propose this cost function here. It's going to be the integral from time 0 to infinity of x transpose times some matrix qx plus u transpose some matrix ru dt. Okay, so here's our cost function here. In this case, we see that x obviously is your n by 1 state vector, right? U is our usual m by 1 control vector. And here, q is a n by n symmetric positive semi-definite, and we'll talk about the definition of that here, matrix here. Sometimes you'll see this written as q greater than 0, or sometimes you might see q like this kind of scripty greater than 0 here. Again, this is a notation for this matrix is positive, yes, positive semi-definite here. And finally, R is a m by m symmetric positive definite matrix. So again, sometimes written as q. Oh wait, I'm sorry. come back to the q here. Positive semi-definite means greater than or equal to. Sometimes it's written like this. To contrast it with positive definite, which means that it, well, we'll get to that in a second. Again, you might see this written as something strictly greater than, or again, this scripty greater than symbol here, right? Okay. Maybe now might be a good idea to discuss what is the definition of positive definite and positive semi-definite. Let's come back to this and let's delete our picture here. I think we understand the scenario that I like to keep in the back of your head. So just keep in your head that, you know, the state vector here, let's think about this as being the state vector for the satellite and the control vector being as the control vector for this particular satellite here. So the concept here with positive semi-definite here, so maybe let's write that down. So positive semi-definite means that this matrix Q, if you took it and multiplied it by some vector x transpose and then multiplied it again by x, this is going to be a scalar number here. If you do the dimensions here, right, this is n by 1 by n multiplied by an n by n multiplied by an n by 1, and excuse me, by the time you transpose this thing, this becomes 1 by n, right? So you can see the whole thing ends up as a 1 by 1 scalar here, right? This scalar quantity is always greater than or equal to 0 for all possible x values here, right? So that's the definition of positive semi-definite, is that this matrix is positive semi-definite if, when you compute this weird quantity x transpose qx, it is greater than or equal to 0 for any value of x, this vector, right? This vector could have positive, negative, zeros, whatever. It doesn't matter. By the time you run it through and compute this, you get something that is is greater than or equal to 0 all the time here, right? Similarly, the definition of positive definite, right, is that again, you have this matrix R here, which we claim is positive definite. The definition is that if you take some vector u, maybe in this case, transpose times u, this is strictly greater than 0 for all u, right? So again, you can work out the dimensions and you see that this is a scalar number here. So here's the definition of positive semi-definite and positive definite. And what's interesting about that is exactly what are the terms of the integrand of the cost function here, right? So you see that the way that this cost function is set up here is that the integrand is always positive or well, actually, yeah, it's positive, right? For any XU combinations here, right? So you can never get a negative integrand. The integrand is always positive. So let's keep that in the back of our head as we continue discussing this, okay? All right, so now that we understand positive definite and positive semi-definite, we have a rough kind of feeling for what this cost function does, right? You can kind of see here that, again, the integrand is always positive, and this Q and this R, those are sort of these weighting matrices or weighting values that we saw earlier when we were looking at our brief introduction to optimization, right? Earlier, the Q and the R were somehow to trade off between time versus money here, right? In this case, we see that Q and R trade off between states here, non-zero states, or non-zero controls. We're going to take a closer look at that in a second, but I wanted to plant that seed in your head right now. Let's start thinking about Q and R as weights to determine how much we value states versus how much we value controls here, right? Okay, so now that we have the cost function down, the overall problem now in this scenario here is, actually tell you, maybe let's do it over here so we can keep talking about the problem here. So here's the cost function. So the optimization problem, let's write this again as our script dp symbol here, right? Is all I want to do now here is I want to minimize this cost function j here, right? But the controls I want to use here, right? There's m controls here. So u is a real valued m valued vector here, right? But we're not. This is not unconstrained here. There's a certain constraint, right? Such that the single constraint that we want to consider here is that, again, x and u are not free to be anything you want here, right? It's x dot is equal to ax plus bu, right? So here is my optimization problem that I would like to solve here, right? And if we think about this long enough, what it's basically saying here is that you want to take this cost function here, and I want to find some control signal or some control law that is going to make this cost function minimal. So first of all, let's stop. Let's think about that first. Ignore the constraint maybe for now, right? How would you make this minimal here? So for example, assume that your satellite had some non-zero initial condition, like x of 0 was not equal to 0. In other words, your satellite was cocked over at some weird orientation and some weird position, not 0, right? Something that you didn't want here, right? So this term is non-zero at time 0, right? Now, if the satellite stayed there, right, if you left it here, like let's draw a quick picture maybe of just one of the states, like x1, right? here's our initial condition, right? So maybe it is banked over at 45 degrees away from where you want it to, right? If you left it here, right, and did nothing, right? What does this cost function look like here? You can kind of see it already. There's going to be a square, there's going to be an x1 squared term here multiplied by this q. Let's assume that q is like all ones or something like that. Effectively, what the cost function there is measuring is it's sort of measuring the integral of this, right? Of course, it's going to be squared. It might be skewed or weighted by that q value. We're going to see that in a second. But long story short here, if this stayed here at a constant value, this cost function is going to blow up to infinity here, right? Because it's the integral from time 0 to infinity here, right? So you can't have this here, right? This is obviously not the optimal thing to do here. You can't leave the satellite cocked over at 45 degrees because that yields a cost function value of infinity here, right? So that's obviously not a good thing to do. So instead, what is better here, right, is we should try to bring the system back to the origin here, right? And now the cost here is finite, right? It's just sort of this area under the curve is the cost value. So this is a better solution than letting it stay at 45 degrees. So what that means is your satellite is cocked over 45 degrees. What we're going to do here is maybe bring it back to 0. That yields a better result here, right? However, the other flip side of that story here is, how are you going to bring the satellite back to 0 here? Well, you're probably going to have to fire some thrusters, right? Some positioning thrusters. You're going to have to expend some amount of control in order to do that here, right? So if we plot again, this is a real rough shooting from the hip description of this. We're going to look at it in a more formal fashion in a second here. But let's just plot one of these controls, like maybe U of t. This is like one of the positioning thrusters or something like that, right? Well, what you're going to probably have to do is if you want to bring the satellite back to 0, you're probably going to have to spend some control authority to do that. And then, again, you're probably going to have to let this come back to 0 here, right? So you're going to actuate the controller, like you're going to bring it back to 0, then you're going to stop actuating the controller, right? So the overall cost function, you can kind of see it's sort of a combination of both. How long are you away from 0 in the states, and how much non-zero control authority did you actually have to expend in order to get that here, right? So what you can see from this discussion here is what Q and R do, or Q and R are these knobs that allow you to determine how much do you care about the state being 0 versus how much do you care about the control not being 0 here. So let's talk about that real quick. In general, right, what you end up seeing here is that, roughly speaking, if Q is big compared to R, so maybe we should write that down here, right? So if Q is bigger, let's put this in quotes here, than R. The reason it's in quotes here is because if you can see Q and R, they're two matrices. They're square and they're symmetric, but they're not even like the same size. So how do you really say one is bigger than the other here? Well, we're going to get to that in a little bit, but you can kind of you can see the gist here, right? If Q is bigger than R here, what are you basically saying? You're basically saying here that I really care that X is not equal to 0, because if so, this term dominates here, right? So in this situation, let me do this in another color here, right? This term dominates. So really, all you're saying here is the important thing in this case here is that if the states are not equal to 0, you end up with a huge cost here, right? Who cares about what the control is? It's really the states that matter and drive this cost function here. So in this scenario, what do we end up with? This is basically saying here, the optimal thing to do here is do what you have to, but make sure those states go back to 0 as soon as possible here, right? So this is typically going to yield something like you would have a fast regulation of X to 0, right? And in order to do that, you're going to end up with U is large, right? So this is sort of the scenario where you're saying control is cheap. I don't care what you do, just make sure the state goes back to 0 really, really quickly here, right? Let's flip that and compare with, what happens if R is bigger than Q, right? So in that case, we have the exact opposite scenario here, right? Where now it's this term that dominates in the cost function, right? So the optimal thing to do here is make sure that U stays as small as possible here, because if U even flinches up or flares up, if you actuate one control just a teeny little bit, this term in your cost function is going to blow up and you're going to end up with a huge cost here, right? So under this situation, the right thing to do here is use control very, very, very sparingly here, right? And who cares what the state ends up doing in this scenario? If the satellite stays cocked over and just takes, hundreds of seconds to come back to the origin, that's fine, as long as you don't fire those thrusters, because the propellant you're expending is extremely valuable here, right? So the behavior that typically ends up happening here is, if you have R bigger than Q here, you have very slow regulation of X to the origin here, right? And U is small, right? So this is really interesting here. So you end up with the first case here, this is like an aggressive controller, right? And down here you have a conservative controller. So we see that Q and R are these knobs that are going to allow us to tweak the states and the controls, or excuse me, tweak the controller depending on how much we care about the states and controls. Let's look at a very concrete example of the cost function, and I think we'll be able to see that here. So for example here, right, let's look at a two-state, two-control system. Right, so what if your satellite here that we're looking at, it only had two states, like we were looking at just the, sorry, let me just write this down so I can talk at the same time here, right? There's only two states, like maybe I only care about the pitch angle and the pitch rate or something like that of it. And then I only have two controls here, like I have a electric thruster and a single momentum wheel or something like that. Right? Okay? And now let's pick values of this Q and these R matrices here. So in other words, let's first start with something really, really simple. Let's make the Q matrix just diagonal, and we'll have a Q11 and a Q22. Let's make zeros over here. Similarly for the R matrix, right? R is just going to be an R11, 0, 0, R22, right? Okay? So these are symmetric, and as long as all of these entries are positive, we'll see that these yield a positive semi-definite and a positive definite matrix here, right? So if this is the case, let's compute this cost function here, or more importantly, maybe let's just compute the integrand of the cost function here. Maybe let's see, what can we do? Yeah, let's erase this. I think we got the picture here. Okay. So now what I want to do here is compute the integrand here, right, of X transpose QX plus U transpose RU. Right, so run to Mathematica and plug all this in here, and what you'll end up seeing here is that this integrand looks like it's pretty simple. It's a Q11 X1 squared plus a Q22 X2 squared. Maybe let's put the squared like this, sorry. Plus an R11 U1 squared plus an R22 U2 squared here, right? So here, I think you can very clearly, explicitly see what do these Q11 and Q2 and 22 and R11 and R22 entries physically mean, right? If you look at this, right, we see that what? Q11 is sort of the weight or the penalty, effectively, on a non-zero x1, right? Because it shows up right here, right? So if x1 is not 0, right, if it's positive or negative, by the time you square it, this term is going to be positive here, right? So as long as the magnitude is not 0, this squared term is something positive. And Q11 is now this multiplicative factor here showing you how much does it matter that x1 is not 0 here, right? It will either exacerbate that in terms of the cost, or it would attenuate it depending on this value here, right? And similarly, let's just go through all of these just to be very, very explicit. So Q22, right? This is the weight or the penalty on a non-zero x2, right? So we very clearly see that the Q matrix, by choosing the entries appropriately, you can now say, which state do I really care about being non-zero, right? I can either say that I really care about x1 being non-zero, or I care about x2 being not zero. Similarly, the R11 term, right? You see it right here, right? This is the weight or the penalty on a non-zero U1 of t, right? And similarly, R22 is just the weight or the penalty on a non-zero U2 of t, right? So R11 is basically, it's actually telling you pretty much exactly how expensive is it to fire or to utilize control number 1, right? This was like maybe your electric thruster. Maybe it doesn't cost you anything at all, right? Because that's the whole deal with electric thrusters, is that electric thrusters are cheap. They are long-lasting, they're reliable here. So if you want to model that fact here in your control design, you can maybe pick a small R11, right? Because if R11 is small, it's basically saying, I don't care what you're doing with this controller. This controller is super duper cheap, because even though if this control is large, by the time I multiply it by a small R11, this doesn't contribute to the overall cost function much, right? And in the same fashion, you see that R22 is the cost of actuating controller number 2 here, right? So that's pretty awesome. This, I think, allows us to set up the entire optimization problem here, right? Now, the thing that's interesting here is now if we start coming back and thinking about the constraint here, right? This is the interesting part. I think we understand the cost function at this point, right? And we understand how to tailor or to tune this cost function using this Q and this R matrix here, right? But the thing that we have to do now is we have to solve this overall problem now here, subject to the linear dynamics of this system here, right? So that's where it gets interesting. So why don't I pause the video, I'll erase the board, and now let's talk about, after we've set up the optimization problem, how can we solve this optimization problem? Okay, so now what we'd like to do here is look at solving the optimization problem. So graphically, what this means here is, again here, we've got our linear plant, right, which is governed by x dot is equal to ax plus bu, right? And now what I want to do is I want to find a control law u here, which is going to make this whole system here optimal here, right? So I'm going to choose a u here so that the x, by the time I look at the combination of u and x in that cost function, it stays small according to the cost function that we set up here, right? So it turns out that the solution to our problem here, so I'll just write this down here. So the solution to our optimization problem here, right, which was, we said earlier, minimize this cost function of integral 0 to infinity of x transpose qx plus u transpose ru dt, subject to these dynamics here, right? This was the optimization problem here. Well, some really smart people figured it out. It's beyond the scope of this lecture today to derive it here, but I think we can use their result here. The solution here is that you better choose a control here that looks like this, minus kx of t, where this gain k here is given by r inverse b transpose s here, and s is the solution to what's called the algebraic Ricatti equation of this. So A transpose S plus SA minus SB R inverse, R inverse B transpose S plus Q equals 0 here, right? Okay, great. And here, yeah, S is the solution to the algebraic Ricatti equation, and also it is its size n by n and square and symmetric. Okay, so this is the solution here, right? So tell you what, if we first ignore everything below here, just look at the solution here, right? The solution is minus kx. We've seen that before. This is just a full state feedback controller. Right? So in other words, the architecture that goes along with this is that this thing just looks like minus k, right? So the optimal thing to do, the absolute best thing you can do to solve this problem is to use a full state feedback controller here. Now, what gets interesting here is that the way you get this k here, you have to go through a couple of steps here, right? If you look at this. So step one here is we got to solve the algebraic Ricatti equation for S here. So let's talk about this. So the procedure for LQR, right? So step one here, right? We are going to be given our A and B matrix, right? Those come from the plan, right? Those are known, right? Okay, they're known and immutable. You can't really change them. The next thing we have to do here is you are going to pick the Q and the R, right? Because you as a control designer, you get to choose how much do I care about states versus how much do I care about control actuation here, right? So you choose the cost function effectively here, right? So let's say step two is choose Q and R. Right? You're basically designing the cost function. Now, according to this, step three here is once I have Q and R, I need to solve the algebraic Ricatti equation for S here, right? So solve, I'm just going to abbreviate this as ARE here, right? So this down here is the algebraic Ricatti equation here, right? Okay, so you solve the algebraic Ricatti equation for S, all right? What you're going to end up seeing here is that once you solve for S, there's actually going to be multiple solutions to S. We'll take a look at this in a second here. But if you follow a couple of steps, you'll be able to find out which is the one you want here. Once you know that here, well, actually, no, I take that back. Let's just say solve this thing for S. You're going to get multiple solutions. Therefore, you can then compute K. You're going to get multiple solutions for K here, right? So you can go ahead and compute your optimal gain K using our expression over there, right? R inverse B transpose S here, right? And again, since there are multiple solutions of S, you'll get multiple solutions for K here. The last thing that you have to do then is typically there's only going to be one solution here that yields a stable situation here. So if you remember earlier with this control of a full state feedback here, right? This thing is basically going to behave at the end of the day like x dot is equal to a minus bk x, right? And this here is like maybe your closed loop A matrix here, right? Again, if this is brand new to you here, maybe take a quick refresher here to our video where we discuss full state feedback controllers, but we showed that under this control law, the dynamics reduce to this here, right? Now, what you can do here is you've got multiple Ks here, right? So that means you have multiple A closed loops. You can evaluate each of these A closed loops and find its eigenvalues, and usually there's only one of them that are going to have all poles in the or eigenvalues in the left half plane here. So let's say step 5 here is choose the K's solution that yields a stable system. Yeah. So that's the workflow that we need to go through. So again, I love concrete examples. Let's look at a concrete example right now to try to implement all this. So the example I'd like to use here is a really simplified scenario. It's a mass and a damper. That's it. Okay, so let's look at an example here of a mass slash damper system. So you got some smooth surface, like, I don't know, like some ice or something like that. You got a mass sitting on this thing. And all we're going to be doing here is let's consider the position and the velocity here, like such. Positive position and positive velocity is to the right here. And let's say that you have a single control of this you're able to exert some kind of force on this block. So you maybe have one rocket engine or one thruster that pushes this block along this ice here. And here there's some viscous damping between the block and the surface here. All right, so I think you can get, without too much of a stretch of an imagination here, that Newton's second law equations of motions are going to basically give you mass times acceleration, right, is equal to the sum of all of the forces here, right? So you got the force here minus the retarding force of the ice here, right? P times C, or sorry, C times P dot here, right? Okay. So without too much, I guess we should say viscous damping with coefficient C, right? That's what this C is here. It's just how much friction you got. Okay, so without too much of a stretch, I think you can turn this thing into a state space representation here by choosing a state vector x of t as, let's make it the position and the velocity of the block. That's our state vector. And the control vector in this case is actually really, really simple. There's only one control. It's this force. Right? Okay, if you do this here, you can basically get yourself a state space representation of x dot of t is equal to 0, 1, 0 minus c over m x plus 0, 1 over m u. Great, that's our state space representation. Here's our A matrix, here's our B matrix here. Let's go ahead and choose some numeric values so we can actually try to compute some of these here. So let's go ahead and how about consider a mass of 1 and a coefficient of damping here of 0.2. So numerically we end up with an A matrix that looks like 0, 1, 0 minus 1/5 here, and a B matrix that looks like 0, 1. Okay, something pretty simple. Now, that is that's step 1 here, right? We got A and B. Okay, step 2 here is let's choose Q and R, okay? So, I don't know, let's pick like a Q of just something really simple. How about an identity matrix here? Later on, we're going to look at some examples where they're not identities. But, okay, Q is identity matrix. R, I don't know, let's choose something like 0.01, something like that. Okay, great. So we got step 1 and step 2 now done. Now we got to go ahead and solve ourselves the algebraic Ricatti equation here. So that's a little bit of a pain in the neck here, right? Because if you remember, that's this long matrix equation. We got to set it equal to 0 and solve for s here. So I don't want to do that on the board. Let's do actually steps 3 through 5 here. Let's just run over to Mathematica and have it do this for us so we can see how can we compute this gain k. All right, so I'm going to pause the video and I'll meet you over on Mathematica.
All right, so here we are in Mathematica. So why don't we go ahead and make a couple of notes here. So what we would like to do now is demonstrate solving the algebraic Ricatti equation and computing an LQR controller K, right? That's our game plan here. So we said, let's first do step 1, right? Step 1 was define the A and B matrix, right? So I think what we said was A was just a very simple, what was it, 0, 1, 0 minus 1/5, I think, and then B was pretty simple, 0 and 1. Okay, there we go. Shift enter that guy, and here's step 1. What was step 2? Step 2 was go ahead and choose Q and R, right? So I think in our situation, we said that the Q was just going to be a very simple identity matrix here. And the R matrix is actually going to be a 1 by 1 of 1 over 100 here. So let me just define it here as a list of lists here. It's just that Mathematica has a little bit of trouble using the parentheses notation to make a 1 by 1 matrix here. So I'm going to just explicitly make a 1 by 1 matrix here. Okay, shift enter both those. Okay, now we're on to step 3, we said, which was solve the ARE, right? So just to refresh your memory here, right, the algebraic Ricatti equation is given by, what do we say it was? I think it was A transpose S plus SA minus SB, R inverse B transpose S plus Q equals 0, right? So we want to solve this for S here. right? Okay, so let's just go ahead and compute the left-hand side of that expression first. So the left-hand side here is what? It's just transpose A times S plus S times A minus S times B times inverse of R times transpose of B times S plus Q, right? So that's the left-hand side here. And maybe let's just simplify. Maybe let's put the simplify up here. Whoops, did I spell that wrong? Simplify here, right? And then let's just look at this thing in a matrix form just to get an idea of this. So, wait a second. Oh, I'm sorry here. We should have defined S here, right? So, we should know here that S is what? It's a symmetric matrix here. So there's going to be an S11, an S12, and this is also going to be an S12 because it's symmetric. And then we'll have an S22. So this is what S looks like here. So maybe let's make a quick note of that here in the Mathematica notebook here. So define S as a symmetric matrix of size n by n, right? Okay, now this second step here is go ahead and solve the ARE. Okay, so let's see, shift enter this value of S here, shift enter the right hand side. Here we go. So here's what it looks like, right? So we see now we basically have, again, this is actually a symmetric equation here, right? Or a symmetric matrix. If you look, this off-diagonal entry is the exact same as this off-diagonal entry here. So really, we have 3 equations and 3 unknowns, right? I need to find S11, S12, and S22 here, right? So what I need to really do now is I need to say solve basically the a bunch of equations, right? It's the left-hand side, the 1, 1 element, right? This has got to equal 0. Actually, all of these entries have to equal 0. So this has to equal 0. The left-hand side of 1, 2 has got to also equal 0. And the left-hand side 2, 2 has got to equal 0, right? So those are this equation has got to equal 0. This has to equal 0. And this has to equal 0 here, right? Those all solve them simultaneously for what? S11, S12, and S22, right? That's what I'm looking for here, right? So if I shift enter this, you see that we actually have 4 solutions like we said earlier, right? That was to be expected. We said that when you solve this, for a lot of times, there are going to be multiple solutions for S. So let's just go ahead and extract those here. So maybe let's assign this to a temporary variable, call it temp, and let's see here. S, let me think about this. How do we want to do this here? You know, actually, we already defined S up here. I know what we'll do. Let's just do it like this here. So, let's call this thing, how about solution 1 gets temp 1. So this is the first set of solutions here, all right? Let's do this for actually all 4 of them here, right? So let's get all 4 solutions here. So let me see, change this to a 4, 3, 2, and then solution 2, 3, 4. Okay, so here's our 4 solutions, and what I want to do now here is make the 4 matrices here. So S1 is going to get S, but I want to make all of these appropriate substitutions. So I'll just say slash dot with solution 1, all right? So here's S1, and great, let's again do this for all 4, 4, 3, 2, and then this should be 2, 3, 4 here. And tell you what, let's just go ahead and suppress the output for all these, and then we will just look at these things as numerical values in matrix form, just so we can get a rough idea of what they look like. Oh, sorry, that should be S1, S2, S3, and S4. So we shift into those. So we see here are the 4 solutions here to the algebraic Ricatti equation. So we need to now identify which one of these are the correct ones. So let's move on to step 4 here. Step 4, which was compute K. All right. And if you remember here, we said that the way we compute K here was K, K is going to be what? It's R inverse B transpose times S here. So we end up with 4 solutions here. So let's do this here. So K1 is inverse of R times transpose B times S1 here. So that's the first possible solution. And let's do this. Let's get all 4 of these guys. 2, 3, 4, and then 4, 3, 2. Okay, great. And then let's look at their actual values here for fun. K1 / n / matrix form. And again, let's look at all 4 of the different controllers that we've now computed here. Here we go. So you can see they're very different here. They have different signs. They have different numeric values here. So theoretically, or at least mathematically, all of these solve the problem. But we know from an engineering standpoint here that they can't all work. Only the ones that have stable closed-loop eigenvalues actually will give us a system which goes back to the origin and therefore has minimum cost in our cost function. So now step 5 here is we need to find solution that yields stable system. So in other words, what I want to do here is I want to look at the eigenvalues of a minus b k, right? And let's call this here. Here's my first set of eigenvalues is lambda 1. And again, let's just go ahead and do this for all of them. All right, so here's lambda 2, 3, 4, and this should be 4, 3, 2, okay, and then let's just look at them all here. So, lambda 1 / n, and let's just do this for all of them. We'll look at numerical values for all of these guys, right? So 2, 3, 4. All right, shift enter that. Here we are. So if you look at this, okay, obviously this one's out. We got a positive pole. We got a positive pole, got 2 positive poles. Aha, here we are. It's actually the 4th solution here, right? The 4th solution gets you a controller which will yield negative poles. So we see that the solution here that we're looking for, it's really K4 here. So here's my controller here that should work. A positive 10 and a positive 10.75.
Okay, great. So we just did this in Mathematica, and we saw that basically this A, B, Q, and R matrix, when you run it through the procedure, yields a gain matrix K of, what did we say this was? This was 10 and 10.76 here, right? So perfect, we designed our full state feedback controller using this technique, but as you saw, it's a little bit cumbersome, right? You got to go through all of these 5 operations here. Luckily for us, Matlab has taken all of these operations here and packaged it up into one function called LQR. So if you pass LQR these necessary inputs, right? In other words, you give it the A, B, the Q, and the R matrix. This LQR function will basically go through this operation and return to you the gain matrix K. It also, I believe, will give you the solution S here that we were solving for, as well as the closed loop eigenvalues of your system here. So in other words, in Matlab, all you got to do here is call LQR, pass it A, B, Q, and R, and it will return to you K, S, and E here. So again here, K is going to be your full state feedback gain matrix. S is going to be the solution to the algebraic Ricatti equation, and E is going to be the eigenvalues of the closed loop system, right? A minus BK, right? Great. So what I'd like to do now here is LQR is, as we see, it's this powerful tool here that's going to allow us to change the behavior of the controller K here, right, by specifying the Q and the R here. So I'd like to investigate now 3 scenarios. So maybe let's make ourselves a little table here. So scenario, maybe with a description, and we'll see what is the resulting K here. Okay, so let's make ourselves a little table here. I'd like to investigate 3 scenarios, 1, 2, 3. So in the first scenario, what I'd like to look at here is, let's go ahead and investigate the situation where control is cheap and a non-zero state is expensive, right? And then in scenario 2, maybe let's get ourselves a little bit more room here. Scenario 2, let's look at sort of the opposite scenario here, where control is expensive and a non-zero, well, maybe I shouldn't, let's write this out. Where control is expensive and a non-zero state is cheap. Okay? And then finally, the third scenario here is, let's mix this up a little bit. Let's say, how about only a non-zero velocity, is expensive. Okay, so in this first scenario, right, you're saying that maybe I really don't care how much control authority you have to exert. I just really want to make sure that the state goes to 0 quickly. The second scenario is the exact opposite, where it's maybe back to our satellite example where you're flying to Mars here and fuel is extremely expensive, but you have all the time in the world to kind of make sure that the satellite returns to its appropriate orientation here. And finally, the third scenario is kind of interesting. It's saying I only care about the velocity. I want to make sure that the velocity doesn't stay high. I really don't care about the position here. So what I'd like to do now is, and actually maybe instead of K here first, let's talk about translating this into an appropriate Q and R matrix. Okay, so you can kind of see in this first case where we're saying control the cheap and non-zero state is expensive here. That's almost like the scenario we just looked at here. So with a Q matrix of an identity matrix 1 1 0 0 and an R matrix of 0.01, right? Again, all we care about is sort of the relative sizes. So you can see here that R is much, much smaller sort of relative to Q. So that should hopefully translate into a scenario where control is cheap. You have an aggressive controller here. And in fact, we saw, let's write down exactly what the gain matrix K was coming out of this scenario here. So we actually just solved this here. So the K in this case was 10 and 10.76. Right? Okay, now let's look at the second scenario here where we would like to flip this. So all we got to do now in this scenario is effectively sort of change the sizing, the relative sizing of Q and R. So maybe let's keep Q the same here. So let's use another identity matrix. But let's just jack up R. We got to make R much bigger than Q effectively. So maybe, I don't know, let's go with 1,000 here, right? And now the question is, what is going to be K? So we're going to run over to Matlab and use LQR to do that. Before we go to Matlab, just so we don't have to break tempo so much, let's fill in a Q and an R for this third scenario here. So in the case where we only want to penalize velocity here, right, we can kind of see that one way to do that here is by choosing your Q matrix appropriately. So for this Q matrix, what we would want to do here is, if I only care about the velocity being expensive, I just got to make sure that the Q entry that is associated with the second state is big relative to the Q entry associated with the first state. So maybe let's do something like this, 0.001 and then 10. So as you can see here, they are clearly mismatched. So the second state will be penalized orders and orders of magnitude more than the first state here, right? And then finally, the R matrix, I don't know, let's just choose 1 here, right? Because in this scenario, all we want to show is the mismatch between the two states. All right, so now that we've set this up, we've got all the different Qs and the Rs, let's run over to Matlab and have it basically, we're just going to call LQR 3 times on each of these scenarios and see what the resulting matrix K is, and then why don't we simulate that using our full state feedback controller, right? Because we said that once you get this gain matrix K, the optimal thing to do here is to have your plant, right? Your x dot is equal to AX plus BU, right? And we're just going to wrap this back through a minus K. And let's use some initial conditions. I don't know, maybe in here, let's use initial conditions of, what did I end up using here? Let me just make sure. Oh, here, something like maybe let's make it pi and -2 here, right? So this is the position. It's pi units away. It's moving at -2 meters per second velocity here. And let's see how fast this non-zero initial condition will be regulated to 0 in these 3 different scenarios.
All right, so here we are in Matlab, and I've actually already typed up this script just so you don't have to watch me inputting it in real time here. And we see that this is really simple. All we're doing here is defining our A and B matrix as we had on the board. And now the Q and the R matrix, we saw that the only difference between the 3 scenarios of where we either want cheap control, expensive control, or the scenario where we ignore the position and only care about velocity, the only difference is the Q and the R matrix, right? Those were our tuning knobs to tailor the optimization problem for our specific desired application. So I've just got a switch statement here where, depending on what scenario we're investigating, I will just load in and define the Q and the R matrix that we discussed on the board. once I've got the A, B, Q, and R matrix, we saw that the entire LQR process is now packaged up into one nice function call in Matlab, namely LQR. So I give it the A, B, Q, and R matrix, and it will give me my full state feedback gain K, the solution to the algebraic Ricatti equation S, as well as the eigenvalues of the closed loop system here. So I'm just going to print that out to the screen so we can see what the controller looks like. And once I've got that defined, we can think about running a simulation to examine how does the system respond under this controller. So I've got just a couple of parameters here, like I'm going to change the final simulation time, and then we're going to define the initial condition of the state space model as we discussed on the board here. So let's build a Simulink model now that will simulate this system. I've got myself a blank Simulink model here saved and ready to go. So it's really simple. The only thing I need to do here is first let's grab ourselves a state space block here and open it up and change the parameters to be A, B, and now the C matrix, right? This needs to be a identity matrix of size 2, and the D matrix is what? It's basically zeros of size 2 by 1, right? All right, so this here now is a state space system that we defined here where the output is just the state, okay? And we'll put in the initial conditions like we discussed earlier. Hit OK, and now the controller, in this case, it's just a full state feedback controller, so it's just really a simple gain here of magnitude minus K, and I just need to change the multiplication from being element-wise to being a matrix multiply, and we basically have now, maybe a better name for this instead of just gain here, is this is our full state feedback controller computed via LQR, right? So this is my LQR controller effectively, right? So let's just hook everything up. Come on, connect. There we go. Connect this up together. And we basically have our simulation ready to go. Oh wait, we should maybe change this for the simulation time. Let's make it T final like we discussed. And also what we probably want to do is send this results back to Matlab so we can analyze it. So let's grab a 2 workspace block. And I will change this to be simx here, and let's change the save format. I just like structure with time better than time series. And let's go ahead and save both the output state here. And then, you know, what we should also do is let's copy and paste this, and we'll get another one, which is going to be simu. And I think we should be good there. And let's hook this up. Whoops, sorry, branch off and hold. There we go. Save this guy. We should be able to now close this model here. It should be ready to go. And now what I'm going to do here is let's just go ahead and simulate the system now. All right, so now let's just go ahead and run that simulation here. So I'm going to call sim intro to LQR, and once that simulation has finished, let's go ahead and extract the data here, right? So time is going to be simx.time, and then x1 is going to be simx.signals. .values, all rows column 1 here, and let's do the same thing for x2 and u1 at the same time here. So extract the second state and the first control here. And now that we've got those extracted, we can go ahead and plot these, right? So let's go figure subplot 311, and let's plot time and x1, and let's make this a little bit thicker so we can see it a little bit more easily. And we'll maybe add a legend as well, just so we can discern which one is which. And let's do the same thing for x2 and u1 while we're at it here. And maybe what we should also do here is, let's add a title to this first subplot here, so we can denote what the scenario is. Okay, scenario, there we go. Okay, great. So this looks pretty reasonable. So let's go ahead and run this script here. And first off, we see, yep, this is the gain matrix K that we computed. It's the same thing that we computed manually. Let's go ahead and look at the solution of the algebraic Ricatti equation. And again, this should be the exact same values that we got with our manual calculation in Mathematica. So this all looks pretty reasonable. Now, let's look at the results here. So remember, this is the scenario here of cheap control. So we see that what cheap control means here is that the system or the controller decides that I better make sure that the states go to 0 fairly quickly. So you see that in just 5 seconds, both the position and the velocity of the system have gone to 0 here. And we spent around, I don't know, what is that, -9, -10 units of force in order to do that here. So Let's compare this now with maybe scenario 2. And maybe what we should do is let's keep this plot up so we can compare. So maybe let's come to the top of our script here and temporarily comment out this close all command. And let's just change our scenario now to scenario 2 here. So scenario 2 is now, let's tell the control system or tell the LQR procedure that control is really expensive now. So if I run this again, you see the K matrix now is smaller. So we have a less aggressive controller here. So if we look at this now, here's scenario number 2. And if we compare that with scenario 1, maybe let's put scenario 1 on the left here, and let's put scenario 2 on the right. You can see the differences in control, right? So now the control system or the LQR procedure realizes that, you know what? Control is very expensive. This is now like rocket fuel that is very costly. So what I'm going to do is the controller is going to allow the state to be non-zero for a longer amount of time, right? So you see over here, it takes almost 30 seconds for the position and the velocity of the block to come regulated back to 0. But the benefit is, if we compare the control that was expended here, you can see the magnitude is much less, right? Instead of having minus 10 units of force, we're now 2 orders of magnitude less here, right? And great. Now, finally, let's look at our third scenario here. So I'll come back to the script here and change it to scenario 3, where we're going to now ignore position. And if I rerun this thing again, you see that the controller changes, and more importantly, the behavior of that controller changes. So now, take a look at this. This is pretty awesome. The control system realizes that, you know what, I better make sure that the velocity goes to 0, so it does that quickly, but it doesn't give a hoot what the position is doing. Look at this. The position is sitting here, and still, after 30 seconds, it's nowhere near back to the origin. But who cares, right? The controller realizes that the position does not factor into the cost function much at all. So it's going to choose a control strategy that only pays attention to what matters, namely the velocity and the control signal here. So this is pretty awesome. If you think about it, we've now got a tool that's going to allow us to translate between physical requirements like which states and which controls do you care about, and then synthesize a controller that will respond and respect those engineering requirements.
Okay, so that was pretty interesting and exciting results. So I think we can come here and we can fill out our table here and finish this section here. So again, we saw the situation where control was cheap and a non-zero state was expensive. We had this type of a controller come out of the LQR process. But now when we change that R matrix, we saw that the control was much less aggressive. I think, 0.03 and 0.12. So yeah, you can just look by the magnitude of these two, you see that this second controller is much more conservative, right? And then finally, the third situation where we only cared about the velocity, it's a little harder to interpret this controller here, but I think we ended up with something like 0.03 and 2.98 here. But again, we might not be able to interpret directly what these numbers mean here, but we saw the behavior was exactly what we wanted here, right? In the sense that the controller drives the velocity to 0 fairly quickly, but doesn't care so much about the position here, right? Okay, well, this is, we're really cooking with gas now, so give me a chance to erase the board here, and we'll come back and apply LQR in another way. Okay, so now that we've got a rough handle on what LQR is and what it can do, let's talk about how about using LQR to address some of these practical full state feedback control issues. So if you remember, this is actually what we discussed in our previous lecture here. So again, I would encourage you to check out that video if you haven't done so here, because I think it will set the stage for this discussion now and you'll have a better understanding of the context. But if you don't want to, maybe just a real quick recap. What we looked at last time where we were talking about full state feedback issues is we looked at a plant model here, which was a DC motor. Right? And the idea with this plant model here was there were two control inputs. There was a voltage on the armature of the motor, as well as an external disturbance torque you could apply to the motor. And what this thing did here is the full state of this system here was the position of the motor, the velocity of the motor, and the current of the motor here. So using this state vector x of just theta, omega, and I, and a control vector u of just VA and this TL, which was the armature voltage and the torque here, we saw that numerically you got an A matrix that we were playing with. It was a 3x3 here. It looked like 0, 1, 0, 0, minus 0.29, and 71.93, and then finally 0, minus 63.24, and minus 1020.35 here. And then your B matrix, we actually were just looking at the B1 here, right? The first column. So what we did here in the example last time is forget about this external torque here. Pretend that this system only has one input, which is the armature voltage. Therefore, the B matrix only has one column, and this is going to be 0, 0, 641.81, something like that, right? Just to give you some numerical values that we can play with now, right? So this here is our model of this motor here, right? And what we said last time here, right, was that you could design a full state feedback controller for this system, but we saw that we ended up with some issues, right? Some of the issues we encountered when designing a full state feedback control system was control saturation, right? And two was the inability to measure all states, right? You couldn't measure the full state. We didn't have a sensor for every single one of these. I think we only had a sensor for one of them, right? So last time we looked at some, I don't know if I want to call them hacks here, but they were ways that you could try to address these, right? We said that full state feedback controllers were incredibly powerful, right? But as Spider-Man's uncle said, right, with great power comes great responsibility. We have to deal with both of these issues here if we're trying to actually implement them, right? Well, LQR is going to give us a technique to directly address this. So let's talk about how can I use LQR to address these two issues here, right? LQR is going to give us a perfect way to do this. So let's look at first, how about control saturation, right? I think the example we showed last time was that if you naively went about trying to place the poles of your closed loop system, right, you could get controls, which was in this case VAs in terms of volts, right? This could spike and this could go down. I think the situation we saw was this went down to like something like minus 90 volts, right? So you had this huge power requirement. So actually in this case, it's with great power comes great electricity bills here, right? So what, you know, if Ben Parker was like, Peter, you can't be doing this, right? Our electricity's going through the roof. Peter Parker should have just said, oh, geez, sorry, Uncle Ben. Next time, why don't I'll use an LQR controller to design my full state feedback system so it doesn't have this problem, right? And we saw the way that manifests itself here is that Peter could just go ahead and vary the R matrix to make this thing as aggressive or as conservative as he wants here, right? So what we can do here is the solution is just use the R matrix to tune, quote unquote, the aggressiveness of the controller. So just as an example here, I'm going to run some numbers here. Let's use a Q matrix of just an identity matrix, right? And then the R matrix is just going to be a single value, right? Let's call it an R11 here, right? And we see that all this is doing now is R11, or this R matrix, we can tune how much do we care about this VA measurement here, right? So let's just make a quick table to show what this ends up being here. So let me R11, let's just make a couple of tables, and then we'll look at the resulting K1, K2, and K3 values that are going to come out of LQR. So what we're going to do right now here is you could run over to Matlab and you can say, Matlab, hey, LQR of A, B, Q, and R. Right? And this is going to spit out the gain matrix K here, right? So I would just like to do a quick little study to see how sensitive is K to R, right? If I change R, how does this change the resultant controller here, right? So I just ran a couple of numbers here. So if you just try 0.01 here, you would get a K of 10, about also again around 10, and about 8.7, something like that. So here's one controller. And this might yield something like this, right, where you have huge power requirements. Well, all you need to start doing then, right, is Peter should have just sat here and cranked this number up and see what happens. So if you crank up R, you're basically saying control gets more expensive. So what happens to the controller? Well, it goes down, right? It starts getting smaller here, right? So you can see it's getting less aggressive. And if Uncle Ben is still yelling at him for costing him too much electricity, he just cranks this thing up again, right? Here, so 1, you would get something like 1.0, 0.93, and 0.34. Right? And then again, just for giggles, let's crank it up even more. So 0.32, 0.25, and 0.05 here, right? So you basically see we get this trend here as R increases, right? The aggressiveness of the controller decreases, right? Decreases. So we see R is this knob. It's literally the knob of depending, you can tell the system how much do you care about each different control when trying to drive the state to 0. Great. Okay, so that's one issue. What about the second issue, this inability to measure the full state of the system? Maybe let's leave this up here. Let's just, tell you what, let's just erase this and we'll go back. Do the same thing here. We'll start from this location. And you can see that it's a very similar story here, right? So problem number 2 here, right, was the inability to measure full state. So unfortunately, this is still a little bit nebulous, even with LQR, right? So if you remember previously in our earlier discussion, right, what we attempted to do was we attempted to identify which eigenvalues were associated with which states here. So let me write this down here maybe. So previously, right, this is without LQR knowledge. What we tried to do was tried to identify or ID which eigenvalues were associated with which states. And again, let's put this word associated in quotes because we saw that you needed some eigenvector analysis to actually do this. And for most systems, the eigenvalues are coupled to multiple states. So they're kind of tangled and you usually can't directly do this here, right? But we tried to do this here because what we wanted to do is once we identified which eigenvalues were roughly associated with which states, we only tried to move those poles or those eigenvalues in the hopes that it would yield a control system which didn't require you to measure all of the states, only to measure the states, or only to use the states which you could directly measure here, right? Well, luckily for us, we can, LQR is going to give us a tool to skip this here, right? Because if you think about this now, right, with LQR, right, I don't care about the relationship between eigenvalues and states because I have a tool or a tuning button that will directly allow me to penalize states directly here. So with LQR, what I can do is I can use Q, right, that Q matrix, to directly specify which states are important or measurable, in the sense that I have a sensor to measure certain states here, right? So now I don't need to do this eigenvalue to state mapping. I can just use Q to directly ask, what states do I care about here, right? Unfortunately, this is still not a perfect solution here because there still is this coupling, right? So again, let's go to an example here. So for example, what we might want to try now is this Q matrix, right? Let's just make this like a Q11 and then zeros everywhere else, right? Because what we're saying here in this case is I only care about the first state, which was the position of the motor, which happened to be the only thing we directly measure here, right? So the hope here is that by just changing this value here, or by only penalizing the state theta, we're going to cross our fingers and hope that the LQR procedure is going to kick out a controller which doesn't really require me to use omega or I much here, right? Again, this is a little bit shooting from the hip here because it's not entirely true. We're going to see that this is the case here. So tell you what, let's use this Q and an R of just 1 here, right? So in this case, we can do our same thing. Let's make ourselves a little table here of what Q11 is, right? And then let's look at the resulting K1, K2, K3. again, by using our LQR technique, right? So, shoot, I didn't leave a lot of space here, but you guys get what I'm saying, right? We're basically going to go here and say LQR of A, B, Q, and R. And this is going to give me the K matrix here, right? But now this Q is, I'm only penalizing this first state here, right? So again, you start here as a small q, 0.01 or something like that. You'd end up with this of 0.1, 0.02, 0.0014 here, right? And actually another quantity that might be useful in this discussion, right? Remember, what we're trying to do here is we're crossing our fingers and hoping that this K matrix, you know, we're trying to implement the control law. The control, which was VA, right, is minus KX, right? What we would really like is if you write this thing out, this is a minus K1 times theta minus K2 times omega minus K3 times I. We're hoping that these K2 and K3 are small with respect to K1 so that we can safely neglect them, and we end up with a control law that is realizable in this case, in the sense that it is gains multiplied by states that you actually measure here, right? So in other words, we're hoping we can neglect these two. So what might be useful here is we actually should maybe, let's look at the ratio of K2 over K1 and K3 over K1. So let's write that down. So K2 over K1 1 in this column, and K2 over, sorry, K3. This should be K3 over K1, right? Because this gives us an idea of how big are K2 and K3 relative to K1 here, right? So in this case, I think you end up with this as about being 0.19 or 19% here and 0.014 here, okay? So in this case, I don't know if I would say this is super great here, because you see that the second gain is almost 20% of the first one. Yeah, this third gain is nice. I think you could safely neglect it because it's only 1.4% of it. But yeah, tell you what, let's start cranking up Q1 here to say this is that theta is really much more important. So again, we can keep working on this table here, right? So move this up, 0.1 here, right? So in this case, you would get a K1 of 0.32, 0.05, and 0.0037 here. So in terms of fractions here, this would be 0.17 and 0.012. So it's going in the right direction, right? The importance is going down. Now it's only 17%. Great, let's keep cranking this up. Let's go 1.0 here, right? So if you go 1, you would get a K1 of actually 1 as well, and then 0.13, and then 0.0092. So in terms of fractions here, this is now only 13% here, and now we're down to less than 1%. So finally, let's do one more just for giggles here, right? So crank K11 up to 10 here, right? So now you get something like 3.16, 0.29, and 0.02 here, right? Okay, great. And now we're down to 0.09 and 0.006. So here we are. So you can kind of see that now in this regime down here, I think this is getting safer to neglect K2 and K3 because it's only 10% and less than 1% of the overall controller here. So again, we see that LQR gives us another tool to try to address this inability to measure full state, but it's still not a panacea here, right? We still get some issues, and there will be some error when you make this neglect here, right? When we neglect these other two terms, you're basically knocking off 10 and 1% of the controller, kind of here, right? Again, you got to worry about what are they being multiplied by. It's being multiplied by omega and I, so this is again a little bit off the cuff here, right? Okay. So this is pretty awesome. I think we had a good discussion, and maybe this is a good spot to leave it. Let's just quickly summarize what we ended up discussing today with our introduction to LQR. So in terms of a summary, right? What did we say? We said, all right, LQR, we see it's a great way to generate a controller that's optimal here in the sense that it solves this optimization problem, right? We said that the whole deal with where LQR came from is we wanted to minimize this cost function J, which was integral from 0 to infinity of X transpose QX plus U transpose RU. dt, right? Let me get rid of some of this other stuff so we can have a nice summary slide. Okay. Okay, so we were minimizing this, and we were picking, at first we were thinking about any control law, or, right, your control can be anything, but then we had to impose a constraint here that really your x's and your u's are not completely free. They're coupled together, and the way they're coupled together is just our linear state transition equation. Right? So you're basically saying, you as a control engineer, give me the Q and the R here, and this optimization problem needs to solve a controller that will respect the dynamics of the system here, right? And it turns out here that the optimal control for this situation that solves this problem here, right? So we'll write the optimal solution is this control law, U of minus kx, where k, right, is R inverse B transpose S here, and S is the solution to the algebraic Ricatti equation that we talked about earlier, right? So we saw that the actual solution here is nothing more than a full state feedback controller where K is computed in a very particular fashion here, right? So what's so awesome about this LQR technique here is that as a control engineer, right, LQR gives us two knobs to directly penalize states or controls, right? So as a control engineer, you choose the Q and the R matrix here, right? And then you run the LQR process here, and it will synthesize a controller for you, which respects these this cost function here and tries to find something that is the best here, right? So Q and R are much more helpful knobs to twist because they have direct physical interpretation, right? Q will literally tell you which states you care about in your system, and R is going to tell you which controls are important or cheap or expensive or whatnot here, right? So I think that's a good spot to leave it here. I hope you enjoyed this video on LQR here. Some of these things set the stage for some of our future discussions, namely linear state estimation is one of the topics we're going to cover in the future. So with that being said, if you like the video, please subscribe to the channel because, like I said, we'll have these future discussions on other controls topics and other engineering issues in the future. So I hope to catch you at one of these future videos. Bye.